Today we're going to be discussing projectile motion in one dimension. One example of this is flipping a coin. Even though it exists in 3 dimensions, it's really only moving in one. It's going up and coming straight back down. This is the simplest form of motion, so this is what we're going to be discussing first. There are 3 distinct components of motion. One is position, which is essentially where an object is at any given time. One is velocity, which is its speed and given direction. And another is acceleration, which refers to speeding up and slowing down. If we assume a constant acceleration, we have these 2 equations for one-dimensional motion. One equation is for position and one is for velocity. The little subscript 0 you see there indicate an initial condition. For example, x0 is the initial position and v0 is the initial velocity. The first example we're going to use is a runner just moving in one direction in a straight line. Let's assume the woman in the picture before is a sprinter training for her track program. She starts at rest and then accelerates at 1.5 meters per second squared. That's 1.5 meters per second. So every second she is speeding up another 1.5 meters per second. What we'd like to answer is how far does she travel in 3 seconds? The question asked how far she ran, so we're going to go ahead and use our position equation. Now in this case, a lot of the terms in this equation are going to cancel out. For example, we'll set her starting position to be 0, and because she starts from rest, her initial velocity is 0, so we're going to end up with a much easier equation for this specific example. And after getting rid of our various zeros, we're left with x equals 1/2 at squared. It's a pretty simple equation, and it's really easy to plug things into. So we know her acceleration is 1.5 meters per second squared, and we're asked how far she goes in 3 seconds, so that's our t value. And we plug in these numbers, and we see that she ends up running 6.75 meters. Excellent! Before we continue, I'd like you to watch this YouTube video. It involves a man walking on the moon and dropping both a feather and a hammer. So go ahead and give that a watch, and then we'll continue with the lesson. In the video, you saw that the hammer and feather fell at the same rate. This is because they're in the same gravitational field, and as such have the same acceleration due to gravity, and that's independent of their mass. The reason it doesn't work on Earth is because of the amount of air resistance and the effect it has on the feather. For the purposes of this course, we're going to ignore air resistance because the problems get really tricky once you factor that in. On Earth, the acceleration due to gravity is always 9.81 meters per second squared for every object, and it's in the downward direction, towards the center of Earth. A lot of times when you're setting up your coordinate frame, you're going to be defining the positive y direction as upward, and because of that, the 9.81 meters per second squared often has a negative sign associated with it as it is in the downward direction. So now we're going to look at another example. One in which graduates often throw their caps straight up in the air, full of jubilation, and then the caps fall back down and the graduates catch them again. Let's assume Pablo is about to graduate, and instead of going to some graduation parties with his friends, he decides he'd rather stay home and calculate how long it's going to take his cap when he throws it up to when he catches it again. So he releases the cap with some initial velocity in the positive y direction. That slows down, it stops, and then it falls back downward towards his hand. And how much time will that take? In this example, Pablo is going to have to utilize both of the equations I presented earlier. If you notice in the position equation, I changed all the x's to y's. That's because we're now considering motion in the vertical direction. It doesn't really matter what direction you're using, the same equation holds true. I just thought I'd change it to y to avoid any confusion, because we generally think of vertical as y. The best way to approach this problem is to break it into 2 distinct parts. In the first part, he releases the cap with some initial velocity upwards, and it goes up until it reaches its peak, and then it stops, resulting in a final velocity of the first part of 0. For the second part, the cap's going to start up at that resting spot and come down until it lands back into his hand. So if we assume an initial velocity for the first part of 15 meters per second, we can plug those values into this equation below. You see the little subscript 1s I put there? That's just to remind us that we're dealing with the first part only, and we're going to have an equation involving subscript 2s when we move on to the second part. So, for this first part, we know the final velocity is 0, the initial velocity is 15 meters per second in the upward direction, and the acceleration is a constant 9.81 meters per second squared in the downward direction. So we plug those values in and find out the time it takes from when he releases it from his hand to when it reaches its peak. We find that to be 1.53 seconds. In order to solve the time it takes for the second part of our equation, it would be useful to know how high it goes in the first place. So we know that his initial velocity for the first part is 15 meters per second. We're going to define 0 to be the position at which his hand releases it. And we know the acceleration, again, is always negative 9.81. So plugging these values in, along with the time that we saw for earlier, we find that his hat gets up to 11.5 meters. Which now brings us to the second part. Huzzah! So we know for the second part, the initial position is up at the peak, and the initial velocity is 0. So up at the peak, it's 11.5 meters. And the acceleration, again, negative 9.81, and his final position we're going to define as 0, back where his hand released it in the first place. So we plug all these values in, solve for t2, the time it takes to fall, and lo and behold, it's 1.53 yet again. And the question didn't ask us how long does it take to rise up or how long does it take to fall. It asked the total time in between when he released it and when he caught it. So all we have to do is simply add up the total time from our two parts. 1.53 plus 1.53 is 3.06 seconds. So after a little over 3 seconds, Pablo's going to be totally ready to catch his cap again. He's going to look really cool in front of everybody in attendance. So that brings us to the class activity for the day. Both Tim and Rick are taking part in the 100-meter dash. Tim decides he's going to run at a constant velocity of 4 meters per second with no acceleration. Rick is going to start from rest or no initial velocity, and he's going to accelerate at 0.5 meters per second squared, and he'll keep that up for the entire 100 meters. The question is, who finishes first, and by how much? So what is their time difference? Get together with a partner and see if you can come up with a solution.